Hello everyone, I'm Dr. Redwan Alqasemi, robotics professor at the University of South Florida, and today I'm going to talk about a comprehensive example that we're going to solve together using all the things and techniques that we learned in chapters 2, 3, 4, 5, and 7 as well. So we're going to look at a 3 degree of freedom non-planar robot. So this will be out of the plane, and it includes 2 revolute joints and 1 prismatic joint. We're going to be going through learning how to use all the techniques to solve this problem. And then we're going to also look at theoretical and programming techniques that we're going to talk about in terms of simulation and how we can make the simulation. Here's the problem that we're going to look at for this comprehensive example. It's a 3 degree of freedom revolute-revolute-prismatic joint robot, as shown here. So this is our first joint. And the first joint variable is theta 1, and that rotates this way here. This is revolute joint. The second joint is another revolute joint with a variable theta 2, and that will be right here, and it rotates this way. And the third joint is a prismatic joint that takes this end-effector in a straight line motion. And the variable for this particular joint is D3. For this example, we are required to do the following. Part A, assign link frames 0, 1, 2, and 3 such that the origin of frame 3 is at the end effector. So we'd like to make sure that frame 3 is at the end effector. Part B, find the DH parameters table. Part C, find the transformation matrices T01, T12, T23, and then T02 and T03. And we're going to need these two transformations later on for one of the requirements for this problem. Part D, using inverse kinematics, find the desired joint values, or Q desired, which consists of theta 1, theta 2, and D3, for the desired end-effector pose defined by the following transformation matrix. So the desired transformation matrix is given here in numbers, both the rotation and the translation. So we'd like to find Q desired that would take us to T desired. And for this, we're going to have to use inverse kinematics as we saw in chapter 4. The length of the link here, we have only one link that has a length, and that length is 3 units. Part E, find the Jacobian J relative to frame 3 using velocity propagation method. And then part F, find the Jacobian J relative to frame 0 using direct differentiation method. Part G, find the Jacobian J relative to frame 3 using force and moment propagation method. So the difference between E and G is the method that we're using to find J in reference to frame 3. Part F, we're finding J0 and J in reference to frame 0 using direct differentiation. Verify that J in reference to frame 3 from parts E and G transforms into J in reference to frame 0 from part F. So we just want to verify that all these three Jacobians, the Jacobian in reference to frame 3 and in reference to frame 0, they're the same Jacobian, but they're in different reference frame. So we can transform one to the other and verify for this part H here. Now remember the Jacobian here, since we have only 3 joints and we have Cartesian space 6 degrees of freedom. So the Jacobians here will be, all of them will be 6 by 3 Jacobians. Now for part I, extract a square Jacobian from J reference to frame 0 that does not have permanent singularity, such that the new J in reference to frame 0 represents the Cartesian linear velocities x dot, y dot, and z dot. So what this means is that we would like to extract out of the 6 by 3 Jacobian here, we would like to extract a 3 by 3 Jacobian. And the 3 by 3 Jacobian should be allowing us to control x dot, y dot, and z dot. So for this particular part of the problem, we need to extract that square Jacobian, so we should be able to invert the Jacobian. Part J, verify that J in reference to frame 0 is invertible for the values of Q initial. Now remember, J always has thetas inside of it, so it's a function of thetas and joint variables, theta and d. So for the values of Q initial, which are given here, Q initial is -45 for theta 1, -22.5 degrees for theta 2, and 8 units for D3. So for these values, find out if J0 is invertible or not. And then find the transformation matrix for that initial joint configuration. Part K, find the end-effector's Cartesian velocity vector that includes x dot, y dot, and z dot. If the robot is commanded to follow a linear trajectory from t initial to t desired in 5 seconds or 100 steps. Okay, so we have the time and we have the number of steps and we have the initial transformation matrix and the desired transformation matrix. So basically we can create a trajectory to go from t initial to t desired. Then find q initial plus 1. So, this means that we want to find the joint positions not at the initial position, but at the initial position plus 1, which means the second step in our trajectory. So q initial is our first step, or 0 step if you want to call it. We would like to find the next step positions of joints. And for this, we need to use inverse of the Jacobian in reference to frame 0. So that will be part of chapter 5. And then write the linear trajectory equations for the Cartesian linear motion, x, y, and z, and the joint motions, theta 1, theta 2, and d3. So these trajectories are based on t initial and t final, or t desired, and the theta is also based on q initial and q desired. Now part I, verify all the answers above using Matlab and Robotics toolbox. So we need to repeat all these problems using Matlab to verify our answers. And then part M, use Matlab and Robotics toolbox to simulate the robot to go from t initial to t desired in 100 steps using iKine. So here we are going to do a simulation and we're going to see how we can go from t initial to t desired in 100 steps. All right, now we're going to talk about the solution in the next slide. Now I can start solving this problem by doing the assignment of frames. So here I put a quick reference for assigning frames and doing the DH parameters. I'm going to start doing the frame assignments right from the screen here. So as a start, I'm going to start with the z-axes, since they are the axes of motion for each one of the joints. So I'm going to start here with joint 1. This is theta 1, this is joint 1. It rotates this way. So my axis of rotation would be the z-axis, which will be right here. We can choose either coming into the board or coming out of the board. So I'm going to choose it to be coming out of the board. So I'll put here a little circle. I'm going to call this Z1. Okay, now for the second axis of motion, I have this as joint 2 right here. It rotates about this axis right here. Okay, so this is my axis for joint 2. I'm going to draw a line from here upwards. And that would be my joint 2 axis. So I'm going to call this Z2. Now for my third joint, it's a prismatic joint. It's going right and left here. So this is my axis of motion. So since it's required that I put my third frame at the end effector, I'm going to draw my z-axis here. And that would be my Z3. Okay, and for Z0, I'm going to just put Z0 identical to Z1. So I'm just going to put it right here with Z1. All right, so now we can go ahead and start with the x-axes. As we can see here in the reference, the x-axes are the common perpendicular between the z-axes. So if I'm going to draw z1, I'm going to have to look at, if I'm going to draw x1, I'm going to have to look at z1 and z2. Okay, so let me start here with x1, common perpendicular between z1, which is coming out of the board, and z2, which is this axis right here. And the only common perpendicular is the line that comes out of here, and it goes perpendicular to both z1 and z2. And that would be my x1. Okay, now for x2, it's the common perpendicular between z2, this line, and z3, this line. So x2 will have to be at this point right here. That's the point of intersection, and it will have to be a common perpendicular between z2 and z3. So again, we can choose it either into the board or out of the board. I'm going to choose it out of the board in this case. So I will circle this line, and this would be my x2. All right, and then for x3, it has to be perpendicular to z3. I don't have z4. So I can take it anywhere on this line as long as it's perpendicular to the line. But to make my calculations easier, it's always better to take it the same direction as x2. So I'm going to put my x3 here. I'm going to circle this and call this my x3. Okay, and then for x0, I'm just going to put it similar to x1 when theta 1 is 0. So that would be x0. All right, and that ends all the x-axes. I have x0 through x3. Now I'm going to go ahead and do the y-axes. And y-axes just follow the right-hand rule. So if I have rotation about z0, and this is x0, right-hand rule means that my y0 will have to be straight up, and that would be y0. And then for y1, again, it's right-hand rule. z1 is out of the board, and this is x1. So according to the right-hand rule, it will have to be along this line. So I'm going to call this y1. Okay. And then for y2, we go to the intersection of x2 and z2. Again, right-hand rule. If this is z2 and x2 coming out of the board, that makes y2 this direction right here. So I'm going to call this y2. And then for y3, again, this is the intersection between z3 and x3. So y3 will have to be going down this way. And that would be y3. Okay, and that completes all the axis assignments. And we have axes from 0 to axis number 3. Now let's see how we can get the DH parameters out of these axes here. So we're going to start with alpha. You know, here we have alpha I minus 1. When I equals to 1, that means we're looking at alpha 0. Okay, and at the same time we're going to look at a I minus 1. So when I equals to 1, that means we're looking at a 0. Again, alpha and a, we can look at here, alpha and a, they always have to look or deal with the distance and angle between the z-axes. So if I'm looking at alpha 0, I should be looking at z0 and z1 about x0. Okay, so x0 here, and z0 is out of the board. Z1 is also out of the board. They both are identical, so that makes the angle between them to be 0. Okay, so that would be 0 right here. Let me change the color to black color. So that's 0. Okay, now for the A, again we're looking at A0. So you have to look at z0 and z1 about or along x0. So this is x0, and z0 and z1 are the same line. So the angle between, or the distance between them, is 0. So that would make this 0 as well. Okay, now let's go to number 2. So we're looking at alpha 1 and a1. So for alpha 1, I'll be looking at z1 and z2 along, I'm sorry, for alpha 1, I'm looking at z1 and z2 about x1. So this is x1, this is z1 coming out of the board, and z2 is up this way. So according to the right hand rule, if you put the thumb at x1 and the rest of your fingers at coming out of the board towards z1, and then go towards z2, that gives me negative 90 degrees. So alpha will be negative 90 degrees. Okay, now for the distance, again, I have to look for a1, I have to look for z1 and z2 about x1. Again, z1 is here out of the board and z2 is right here. They both intersect. That means the distance between them is 0. I'm going to look at when I equals to 3, so I'm looking at a2 and alpha 2. So let me start with alpha 2. So alpha 2, I have to look at z2 and z3 about x2. Again, z2 is here, z3 is here. So I have to look about x2. x2 is coming out of the board. So to go from z2 to z3, I'll have to do negative 90 degrees as well. So that would be negative 90 degrees. Okay, and then for the offset here, I'm going to be looking at a2 between z2 and z3 along x2. So this is z2 and this is z3, they intersect. That means the distance between them is 0. Okay, and then the last elements here are when I equals to 4, so that will be alpha 3 and a3. So for alpha 3, I should be looking at z3. Actually, we don't have a fourth, so this is out. We don't have a fourth. We put here our third frame as our end effector frame. So there is no line up here. Okay, now let's go to the d and theta, di and theta I. So when I equals to 1, I'm looking at d1 and theta 1. And we look at these two quick references. So let me start with d1. I should be looking at x0 and x1 along z1. Okay, so this is z1. I'm looking at x0 to x1. Both of them are intersecting at this point, which means that the distance between them is 0. So that would be a 0 here. And then the angle between x0 and x1 about z1. So that's the angle between x0 and x1 about z1. And that angle will be a variable, which is represented by theta 1. So this here will be theta 1. Okay, now we go when I equals to 2. So I'm looking at d2 and theta 2. I'm going to start with d2. I should be looking at x1 and x2 about z2. This is x1 and x2 is coming out of the board about z2. So again, this is a distance between this line that's coming out of the board and this line, which represents x1. And that distance here is an L distance that we can see here. Okay, so I'm going to put here L. Okay, and then for the angle, I should be looking for the angle for theta 2. I should be looking at x1 and x2 about z2. So x1 is here and x2 is here, and that's about z2. So this angle is a variable angle, and the angle is represented by theta 2. So I'm going to put theta 2 right here. Okay, now for the last line here, I'm going to look at I equals 3. So this is d3 and theta 3. So for d3, I'll be looking at x2 and x3 along z3. This is x2, this is x3, both of them coming out of the board, and the distance between them is this distance. Now remember, this here is a prismatic joint, so this distance is a variable. And if the prismatic joint goes backwards, these two lines that are out of the board will become closer. If it moves forward, then these two lines will go further apart. So this is a variable that's represented by d3. So I'm going to put d3 here. Okay. And the last thing is theta 3. So I'm going to look at x2 and x3 about z3. So x2 is here out of the board and x3 is here out of the board. They're both the same direction and there's no revolute joint between them. So the angle between them is a constant, which is 0. Okay, and that completes our frame assignments, which is part A, and our DH parameters, which is part B. In this slide, I'm going to show here just the figure in a more clear way, where we have the frame assignment and the DH parameters table. And I have also kept the quick reference here for how to find the DH parameters between the frame assignments. In this step, I'm going to just put here a reminder of the DH parameters that we found earlier. And here we just need to find the transformation matrices for our robot. So starting with T01, we can use the general formula, or we can use the way we used this before, where we multiply rotation about x by the amount of alpha, and then multiplied by translation along x by the amount of a, and then multiplied by rotation about z by the amount of theta 1, and then multiplied by translation along z by the amount of d in this case. So we can do the same for each one of these lines in the DH parameters to find each corresponding transformation matrix. So we can find T01 from the first line when I equals to 1, and then T12 from the second line when I equals to 2, and then T23 from the third line when I equals to 3. Then to find T02, we just multiply T01 times T12 to find T02. And to find T03, we can multiply T02 times T23 to find T03. Part D here is inverse kinematics, and we are required to find Q desired when we are giving T desired. So the desired transformation matrix that the robot has to go to, we can use that to find Q desired that would take us to that location. So here I put side by side two matrices. The first one is the general form that we found through forward kinematics, this transformation matrix. And then this matrix here is the desired transformation matrix that was given in the example. Okay? And all we have to do for inverse kinematics is try to find equations that we can equate some elements from here to some elements from here. And then solve these equations to find theta 1, theta 2, and d3. Okay? So now let's look at the first couple of elements. I'm looking at R12 and R22. That's this element here and this element here. And the reason I chose these, not these, for example, is because both of these elements include only theta 1. So I don't have to worry about having other variables and having to get rid of these variables before finding theta 1. So for these two elements, their equivalent here in this matrix are these two elements. So basically sine 1 equals to 0.707, as we see here, and negative cosine 1 equals to negative 0.707, as we see right here. Now that we have sine 1 and cosine 1, we can use a tan 2 to find theta 1. And again, a tan 2 is a function in Matlab that's available. It's similar to inverse tan, but this function here preserves the sign of the sine and cosine. So this way you know which quadrant you're in instead of having random solution, because this would have two solutions if we don't use a tan 2. In this case, a tan 2, you can put the two inputs here. The first input is the sine, the second input is the cosine. So we input these two here to find the theta in the right quadrant. In this case, theta 1 turned out to be in the first quadrant, since both of these are positive, and this was 45 degrees or 0.7854 radians. Now for theta 2, I'm going to look at R32 and R33, and these are right here. R32 is negative sine 2, and R33 is negative cosine 2, and their equivalent in this matrix are 0.866 and 0.5. Okay, so I'm going to put these negative sine 2 equals 0.866 right here, and negative cosine 2 equals to 0.5 right here. Now remember, I need to get sine 2 and cosine 2, so both of these negative signs have to go to the right side of the equation. Now from this, I can go straight to find theta 2 using a tan 2 again, and I put the amount of sine here, and I have to include the sign, make sure I include the negative sign, and then the amount for the cosine, and also include the sign for it as well. So because both of these are negatives, this equation is going to give me directly the right angle, which in this case would be in the third quadrant. As we know, both of them are negative. So that angle turned out to be negative 120 degrees or 2.0944 radians. Okay, so that would be my theta 2. Now for the third joint variable, D3, I'm going to look at R34, which is right here, and its equivalent in the given desired matrix, which is 2. So basically negative D3 C2 equals to 2. And from that I can extract D3 to be equal to negative 2 over cosine theta 2. Okay, I already have cosine theta 2 value, which is negative 0.5 right here. Okay, so I can just substitute and find D3 to be 4 units for this robot. Now, I have theta 1, theta 2, and D3. I can just put here Q desired equals to 45, negative 120 degrees, and 4 units. Okay, and these values can be put either in degrees or in radians. Now, we have to make sure that whenever we use Matlab, we have to be consistent also in our convention of using units here. If you use radians, make sure you always use radians. If you use degrees, make sure you always use degrees, and convert from radians to degrees whenever needed. Now, just to go backwards and check my answer, if I plug in these theta 1, theta 2, and D3 into this matrix that we found from Fourier kinematics, okay, I should be able to find the desired transformation matrix. Okay, so if I plug T03 from here, and I substitute theta 1 by its value, and theta 2 by its value, and D3 by its value, and sure enough, I got a matrix that would be exactly similar to this matrix.